Okay, so Roshan also has to join, right?
Sir, Roshan actually informed Navakumar that he has some internet issues.
Oh, he has some internet issues.
Yeah, he said, inside the second lecture, when he meet for the second time today, he got disconnected in between.
Oh, he got disconnected. Okay. All right. All right. Okay, so let's continue then. So let's continue. Okay, so let's xi b and t theta tm, and let's choose a curve zs. Mm, so s maps to little zs equal to alpha s capital Zs in Tm. So be such that Z prime 0. So Z0 is equal to theta. Z prime 0 is equal to xi. And again, we let f of st be x sub alpha s of t zs, and j of t is the usual Jacobi field. So this is del del s at s equal to 0 of f of st. Okay, fine. So right. So what's the picture? Well, it's the same picture we've been drawing before. So okay, so here's my gamma, which is gamma naught, and here's my gamma s. Here curves like this, and so here is my initial tangent vector theta, and this is what I get after flowing by time t. This is phi t of theta. Okay, and here is my initial tangent vector to gamma s. So this is little z of s. Okay, and when I come over here, this is what I get by flowing phi t of little zs, right? Yes?
Yes, sir.
Yes, sir.
So what will the differential d phi t of z prime 0 be? It will be just I differentiate this tangent vector with respect to s, right? At time t. Yes? It
Yes.
will be del del s of phi t of zs, right? It will be del del s of phi t of zs, right? So what is d phi t of xi? this is d phi t of DDS at S equal to 0 of ZS. So this is equal to del del S at S equal to 0 of phi t of ZS. Right? So what is phi t of ZS? Phi t of ZS is, this is del del S at S equal to 0 of the tangent vector gamma S t, gamma S prime t, right? Yes?
Yes, sir.
Okay. So now we have to apply the isomorphism little j sub phi t theta. So we have to take the horizontal and vertical components of d phi t xi, right? We have to take the horizontal and vertical components. So actually those will come by looking at this Jacobi field. The horizontal component is easy. It's just how the foot moves. So the movement of the foot is just the derivative of this curve, right? This horizontal curve here. Right? So that will be exactly the Jacobi field at time t, right? Yes? So if I look at j of t, what is j of t? J of t is del del S at S equal to 0 of gamma S of t. And gamma S of t is nothing but pi of phi t of ZS, right? Yes? Yes, is this right?
Yes, sir. This is okay.
This is fine, yes? Okay.
Mhm. Yes, sir.
So by the chain rule, what is this? This is exactly d pi at the point phi t of theta applied to d phi t of the derivative of ZS at 0, which is xi, right? So that gives us one equality. Jt is equal to the horizontal component of d phi t xi, right? Now we have to look at the vertical component. So for that, let's look at j prime t. And again, we'll use symmetry of the connection. So j prime t, this is d del t of del del S at S equal to 0 of f of st. So by symmetry, this is d del S at S equal to 0 of del del t of f of st, right? Okay. So this is d del S at S equal to 0 of so del del t of f of st is this tangent vector gamma S prime t, right? So this is del del S at S equal to 0 of gamma S prime t, right? And note that d phi t of xi, this is equal to, I mean, rather, yeah, this is equal to del del S at S is equal to 0 of gamma ST gamma S prime T. So what is this? This gamma S prime T for T fixed. This is a vector field along the curve. S maps to gamma S of T. Here T is fixed and S is varying, right? So, so this is an element of the tangent. This is a curve in the tangent bundle for T fixed. If I vary S, S goes to gamma S of T, gamma S prime of T, right? And so I'm taking the covariant derivative with respect to S of the vector field along this curve at time 0. That by definition is the connection map at phi t of theta applied to the tangent vector of this, which is d phi t psi. Is this clear? This is by definition of the connection map, right?
Yes, sir.
Yes, sir.
Okay. So that's it. So that proves what we want, right? So thus, so we already know that J0, J prime 0 is equal to J theta of xi and JT, J prime T is equal to J phi T theta of T phi T of xi. Is this clear? So that finishes the proof, right? Yes?
Yes, sir.
Yes, sir. Yes.
Okay. So the derivative of the Jacobi of the geodesic flow is written in terms of Jacobi fields. Right? As basically J0, J prime 0 maps to JT, J prime T. That is the derivative of the geodesic flow. Is it clear? Yes, so to get the derivative of the geodesic flow, you basically have to solve a second order equation, right? So you take VW, that gives you initial conditions J0, J prime 0. You solve and you get a Jacobi field, and then you look at its initial conditions at time t, which is JT, J prime T. And so the differential of the geodesic flow maps J0, J prime 0 to JT, J prime T. Is it clear?
Yes, sir.
Okay. So it's just this picture here. You look at this picture and you can see it. Yeah, I mean, these are two, when S is small, these are two infinitely close tangent vectors in TM, this theta and this ZS. And I'm applying the geodesic flow to both of them, phi t, right, to move up time t along these two geodesics. So when they get infinitely close, the difference between these two will be given by the derivative of phi t applied to these two, right? And the difference between these two is the Jacobi field, right? It's just the Jacobi field. You get it?
Yes, sir.
Okay. So that's the idea. Okay, so Utsav, does this help answer your question why we are interested in Jacobi fields?
Yes, sir. Yes.
Yeah, because we can write, for one thing, the derivative of the geodesic flow exactly in terms of Jacobi fields, right?
Right.
And this is important because using this, you can tell whether the geodesic flow is it expanding in certain directions or contracting in certain directions in the tangent bundle. Whether it expands or contracts, that will be given in terms of the expansion or contraction of the derivative of the geodesic flow. And that will be given in terms of, now you can see, in terms of growth or decay of Jacobi fields, right? So if the Jacobi fields are growing fast for certain initial conditions, then that means in those directions, the derivative of the geodesic flow is expanding, right? So the geodesic flow is expanding in those directions. And conversely, if the Jacobi fields are decaying, then in those directions, the derivative of the geodesic flow will be contracting, right? Okay.
Yes, sir.
Yes, sir.
So as a corollary, right, so okay, so in these pictures, you're seeing the Jacobi fields, they look perpendicular to the geodesic, right? But you can have Jacobi fields in the direction of the geodesic also. So, so note there are always two Jacobi fields.
Speed of the geodesic is a Jacobi field.
The velocity of
The
the
velocity
exactly.
vector, yeah.
The velocity vector is always a Jacobi field, correct? That's right. That's right. So let's just observe. One J of t equal to gamma prime t is a Jacobi field. Since J double prime plus R of gamma prime J gamma prime, this becomes equal to, so J double prime will be gamma triple prime, that's 0, right? So because gamma double prime is 0, right? So this is ddt of gamma double prime, which is 0, plus R of gamma prime, gamma prime, gamma prime. And R of gamma prime is 0, right? Because R is alternating. Yes?
Yes.
Yes, sir.
Therefore, this becomes 0 plus 0, which is 0. Now, we know that any Jacobi field, it corresponds to an element of t theta tm. In other words, it corresponds to a deformation of the initial tangent vector, right? So what deformation does this correspond to? What is the parametrized surface here in this case? So if this is my gamma prime 0, my Jacobi field is moving parallel to gamma, right? So what will my parameterized surface be? This is my J is moving in this direction. So what will my parameterized surface be?
It will be the curve only.
J corresponds to what geodesic variation does J correspond to? What will it be?
exp of gamma t of
Right. So
gamma
let me
prime.
just write it this way. F of st will be what? Gamma. It'll just be gamma of t plus s, right?
Yes, that's it. Yeah.
That's all. It's just translation along the
Mhm.
geodesic.
Hmm.
It's translation along the geodesic, right?
Yes.
Yeah. Yes.
Yes, sir. Yes.
So here del s at s equal to 0 is equal to j. Is this clear?
Yes, sir.
Yeah. And as an element of so j element of j gamma, this corresponds to, so what is j0 is just gamma prime 0. So let me write gamma 0, gamma prime 0 equal to PV, which is theta, right? So then this corresponds to this J0, J prime 0, which is V comma, J prime will be gamma double prime, which is 0. So it's V comma 0, right? In TPM, direct sum TPM. And that corresponds to the geodesic vector field, right? G theta in T theta Tn. Is this clear? So
Yes,
this
sir.
corresponds to the element G theta in T theta Tn, this vector field J. All right. Is it clear?
Yes, sir.
Okay, now there's another vector field which is in which is also tangent to gamma. What is that? Can you think of it? What will that vector field be? Any guess? So here we're basically moving the this basically we're moving the foot along gamma, keeping the head constant, right? That is what this variation of is, right? That's what the geodesic vector field is. You move the foot, keeping the head constant, right? Yes. Move the foot
Yes.
in the direction of the vector, keeping the head constant. Now there's
Mhm.
another. So here I'm not moving the head. I'm just moving the foot. So what's the opposite thing? I can keep the foot fixed and just move the head, right?
Hmm.
In the direction of gamma,
Mhm.
right?
Right.
Right. So so that would correspond to what? That would correspond to increasing this tangent vector, multiplying it by t, right?
Okay.
Yeah. So 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 let me know. First, let me write down what the variation would be. F of st. So if I keep the foot the same and I increase the velocity, what am I doing? I'm just changing time along the geodesic, right? It means I'm multiplying time by s, right? It would be gamma of st. Do you understand?
Hmm.
Right? So
Hmm.
what do I get if I differentiate this with respect to S at time 0? I'll get T times gamma prime T, right?
Hmm. Yes. T times gamma.
Wait 1 second. Let me just think about this for a second. Hmm. No, when S is 0, then I should get gamma. So this should be gamma of ST plus T. I think this will work, right? I mean, what I want is the Jacobi field T gamma prime T.
Hmm.
Okay, because
Yes.
what is J prime? J prime will be 1 into gamma prime plus T into gamma double prime. So it will, J prime will be just gamma prime. And so J double prime will be gamma double prime, which is 0.
Hmm.
Okay. And so my J double prime plus R of gamma prime J gamma prime, this will become 0 plus R of gamma prime T gamma prime gamma prime. So this is 0 plus T of R gamma prime gamma prime gamma prime, which is 0.
Equal to 0.
So this is the Jacobi field. Okay. And I think it corresponds to this, right? When I put S equal to 0, then I get gamma of T.
Hmm.
And when I differentiate with respect to S at S equal to 0, what do I get? I'll get,
T times gamma prime.
I should get T times gamma prime, right?
Yeah. That's what.
Yes, I think this is correct.
Yes.
Yes.
Yes. Yeah. If I keep T fixed, then differentiating, I'll get T times gamma prime.
Differentiating with respect to S at time 0, I'll get T times gamma prime, right?
Hmm. Yes.
Is this okay? Yeah.
Yes. Yes.
So here, what is the corresponding element of T theta Tm? So J over here in J gamma, this goes to J0, J prime 0. This is exactly, J0 is going to be 0 because of this T here. This is 0. And J prime 0 is exactly gamma prime. So this will be 0V in TPM direct sum TPM. So this corresponds to, okay, I'm using J for too many things, but you know what I mean. Capital J theta, the complex structure of, almost complex structure of T theta Tm. So this corresponds to J theta of G theta in T theta Tm, right?
Hmm.
So the first one is a horizontal vector in T theta Tm, V comma 0. The second one is a vertical vector in T theta Tm, right? This is a horizontal vector. This is a vertical vector. Is it clear? Yes?
Yes.
Yes, sir. Yes.
Yes.
Okay.
Yes, sir.
So we know that T theta Tm I can write as, so let me take a theta equal to PV in T1m. A unit tangent vector. Okay, so mod V is equal to 1. So then I have this decomposition of T theta Tm, right? T theta Tm was R G theta direct sum R J of G theta right? Direct sum, the perp of these two. Yes. Okay.
Okay, yes, yes.
And what is the perp here? So the perp is basically, this is this is equal to xi in T theta Tm such that so if you're perpendicular to R G theta, then that means inner product of d pi theta xi with V is equal to 0. And if you're perpendicular to J theta of G theta, that means inner product with 0 comma V is 0. So that means inner product of K theta xi V, this is also 0, right? Yes? Okay.
Yes, yes.
Now, what is this space? So the second equation, that K theta xi V equal to 0, this tells me what? This was exactly, this means the vertical component of xi is perpendicular to V, right? That means the head is moving perpendicular to V. So that means the length of V should not change, right? If I move the head perpendicular to V in V perp, then the length of the head doesn't change infinitesimally. Yes? It's just this picture. Here's V, and I'm moving the head perpendicular to V. So infinitesimally up to first order, the length doesn't change, right?
Yes, sir.
So this means this is the tangent space to the unit tangent bundle, right? The length stays 1. So this part tells me that I am in T theta of T1m, right? And this second part is telling me that my canonical 1 form, this is the canonical 1 form, alpha applied to xi, right? This is alpha theta applied to xi. Yes? So this is nothing but the kernel of alpha theta restricted to T theta T1m. Is this clear? Yes?
Yes.
Okay, we've seen this before. We've seen this before. Yes? So this is a 2n minus 2 dimensional subspace, right? Of T theta T1m, which is 2n minus 1 dimensional. Right? This is the contact distribution. Yes? The kernel of alpha we showed was a contact distribution.
Yes, yes.
right? Are you remembering now? Yeah.
Yes, sir.
Okay. So what are these in terms of Jacobi fields? What is this? In terms of Jacobi fields, okay, so in terms of Jacobi fields, this kernel of alpha theta, so we call this S theta. So S theta this corresponds to, so xi in S theta, this corresponds to a Jacobi field J in J gamma, such that, so the initial conditions of J are J0 is d pi theta xi. So J0 should be perpendicular to V and also J prime 0, right? Right? Okay. Is this all right?
Yes, sir.
Can you please explain once more the last line?
Sure, because this S theta is what? It means that d pi theta xi inner product with V is 0 and k theta xi inner product with V is 0, right?
Or then d pi theta xi is J0 and the other one is J prime.
Exactly.
Okay.
Exactly. That's the correspondence, right? Is it clear now?
Yes, sir. Yes, it's clear.
Okay. So, so what we get is that basically any so let me call this J let me just call this J0 of gamma. Okay. Let me call this J0 of gamma. So what we get is that thus any Jacobi field, we can write it as R gamma prime. Okay, let me end this meeting and start a new one. There's less than a minute left. I'll just talk for another 5-10 minutes. Okay, we're almost done.